Hi everyone, I'm Gail Eckert, Director of Marketing for Qualmark, and will be the moderator of today's event. I'd like to thank you all for attending today's Ask the Experts presentation. Qualmark, the global leader in accelerated stress test technology, sponsors these series of webinars to expand knowledge about the many benefits HALT, HAS, and HASA can bring to your reliability program. For additional information, please visit us online at qualmark.com. Today, Kurt Gray will provide answers to the top 3 questions most often asked about HALT. Why should I test beyond specifications? If it fails beyond spec, why should I care? And can HALT find software defects as well as hardware defects? With his 30-plus years in the electronics industry and 15-plus years of HALT testing expertise, Kurt knows from firsthand experience why it is so important to HALT products. Kurt is a senior collaborator with CALS, the Center for Advanced Lifecycle Engineering, and is a reliability test consultant providing effective insights and solutions for improving the reliability of electronic systems. He's also available for seminars and training. You can find Kirk on the web at www.acceleratedreliabilitysolutions.com. Welcome, Kirk.
Thank you, Gail, and thanks everybody for joining our webinar today. Hope you find it useful. Looking forward to a great summer coming up and Memorial Day holiday in this next weekend. Hope everybody's looking forward to a good vacation. So you can see here, I began in this field actually 20 years ago, where I met Dr. Greg Hobbs, and had the most fortunate time working with him at Storage Technology and learning about HALT and HAS long before I learned about the traditional reliability engineering approach. Like Greg, I'm not a certified reliability engineer, as HALT is a very significantly different frame of reference and a paradigm in reliability improvement. Okay, I'm going to start out with a little bit of humor here. I think Scott Adams almost wrote this, created this comic for me. It was published on the Saturday. I know all of you, a lot of engineers are Dilbert fans. And this is probably the reason why we're still in the mode of where we are today with traditional reliability engineering. Trying to put together all the equations and requirements that it would be necessary to predict life in electronic systems is nearly impossible, plus the life cycle stresses that any product goes through is also hard to predict. And that really comes up with, still we're using a lot of hallucinated assumptions about electronics reliability and how to achieve it. Why test beyond specifications? Why stress beyond specifications? Well, the main reason is because stress margins are proportional to reduced warranty rates. Here's an excellent and one of the very few nuggets of data from Cisco Systems. Dr. Ed Kaiser presented this at the workshop on accelerated stress testing, which we'll talk about a little later. There is a meeting coming up this September. But anyway, this graph shows a comparison with the normalized field return rates and the operating degree C operating margin on the products, on these Cisco line cards. And comparing using this scatter diagram and putting a best fitting curve to it, you can see you have a probabilistic slope described here in this equation. Now, since the more margin, and here it has a 50 degree C margin data point, you can see significantly reduces the warranty rate. And When you come up with an equation like this, you can actually perform a return on investment analysis on increasing margins. 30 to 40 degrees C margin would have a probabilistic effect of decreasing the warranty return rate by this much. And because of that, you could actually, since you know the cost of warranty returns, you could actually come up with a dollar figure for how much a 10 degree C or 20 degree C increase in margin could probabilistically give you. Of course, the old adage is a chain is only strong as its weakest link, and certainly it's true with electronics. Electronic systems are only as robust as the weakest component. And like this chain, most electronics have a very significant strength. It's very difficult in my 20 years of trying to break electronics with HALT. It is significantly difficult to actually cause catastrophic failure. You do get to limits you can find limits very quickly, and limits are important, not just necessarily a hard failure. But you have to pull it until it breaks. You have to find the limit, the empirical limit. We want to first make sure we get the definitions in order here. What you'll mostly find in HALT, and especially in digital hardware, is the operational limit. And that's the empirical limit, not a theoretical limit, but an empirical limit where you actually test the unit and increase the stress until you find it's stopped operating. And that is with, of course, all the overtemperature protection mechanisms defeated if possible. Sometimes sometimes they're built in and difficult to remove, such as the CPU. And in that case, we would use a water-cooled block to prevent the thermal trip of the CPU, with the rest of the system being able to operate anywhere from 110 C to up to 130 C of upper temperature margin. The other limit you may find, and sometimes find, especially in more likely in vibration, is a destruct limit. And that's catastrophic, where you have to remove a part or replace something before you can get it to operate again. And as I say, destruct limits are rare, especially in thermal HALT. It's more likely with power supplies, but still very difficult. And it's more possible with vibration or voltage, but I have vibrated many power supplies at the top capabilities of HALT chambers, and they survive for a significant period of time. HALT testing, we want to basically have a very quick review of what it is. It's called a highly accelerated life test, but it's not a life test at all. It's conceptually simple. It's basically a step stress test. We use a single stress when you're beginning to do HALT. You want to start out simple to make it easier to analyze the cause of the failures. And generally, we start in an order of cold first, heat, and then vibration and or voltage, but using each one to understand each limit that entails. Steps are 5 to 10 C for thermal and 5 to 10 G's RMS. But when you get to the first destruct level, you might, as you get close to the anticipated level, you might do smaller steps to get a better resolution of where those limits might be. We want to stress again to empirical operational limits, and sometimes that is a destruct. Now you have your functional time here that you make sure that you're testing when the product has reached somewhat of a thermal equilibrium, but you'll also find as you develop the skills in HALT that transitions will be important too, but at the first, just simply being able to ensure that you can have a significant test coverage during this period at least. So your steps may be more than 10 minutes if you're if your diagnostics takes longer than that. So if you can, you want to find the root cause. It's not always possible. You might identify the root limiting component, and if that's the case, then it may be easy just to replace that component with a higher power component or higher capability component. And you want to go up to the standard materials, just using standard materials processes. What we call the fundamental limit of the technology. Increase the operational margin till you can reach the fundamental limit of technology. You will find that you'll set in your own mind a benchmark. Once you start testing your own products and finding limits, then you'll set a new standard of what you should expect the next generation product to be able to operate to. After you start doing one stress, then it's important to also add a combined stresses. And of course, this is an absolute must in what would be a screening process, a highly accelerated stress screening. Some of those stresses could be thermal, voltage, clock frequency changes, vibration, and even in the IT industry, you would want to use different software applications, different functions such as graphics or hard disk accesses. And just to mention how a single part can increase the margins, with Advanced Energy Industries, we changed 100 amp switch to 150 amp switch in the device, in the power supply that they were manufacturing, and got a 23 degrees C margin. Generally, it's only one or two components that need to be changed to increase the margin. There's been a lot of talk in the past, and certainly in the 20 years, everybody thinks about HALT and the life test, and that you should be able to come. A lot of people thought, well, this comes up with an MTBF number or a lifetime number in the field. And the reality is there is no single or combined accelerated test that can give you a system's lifetime equivalent. I've circled here some of the mechanisms that, or some of the devices that you'd have to model and and have an understanding of to be able to give a lifetime number. You've got a VIA, all these devices, these solder joints, this probably an MLCC, are all going to fatigue at different rates depending on whether this IC, what temperature it reaches, where it's placed on the board. The VIA is going to fatigue and crack at a different rate. All of them have a different rate in response to the end-use environment. And you'd have to know a tremendous number of SN curves, various values for the Arrhenius equations, if it's even relevant, and many times it's not. In fact, most of the time the Arrhenius equation is not a valid mechanism or driving these mechanisms. Here's a personal experience, and talk about long life in electronics. Our kitchen radio, my father bought this back in 1978, handed it down to me. It's going to last forever. It may outlast my life. But 35 years, and you know, I'm sure the MTBF prediction was quite short, and certainly not 35 years. But all of our electronics have more life than we need, and we need to start to be efficient at developing reliability. We need to be using that life and using the capabilities, very broad stress capabilities that are in most electronic system assemblies. When I talk about electronics here, I'm not talking about individual discrete components. I'm talking about, and the HALT testing, it has to be performed at a circuit board and operating system level of some sort, motherboard, a graphics card, something like that, or a small power supply. Okay, here we have some components that got the smoke left out. Got the smoke let out. This is a hard failure, of course, and these are fairly rare in HALT testing. You'd be surprised how rare you find these, but it can happen when two components may short together in vibration. It is pretty rare in thermal HALT, but it sure makes it easy to identify the problem area when you do find this struck limit happening. So we really are, a lot of people are worried much more about these kinds of failures and that they're going to have completely destroyed equipment at the end of a HALT test. And certainly not, this isn't the case with thermal. And even vibration, it's very difficult to do. But you do find limits, and you will find, most likely in vibration, a component leg breaking off or a cracked solder joint that just causes it to fail to operate, not as massively destructing as this. Now this is a bigger problem, a soft failure. It's very difficult to detect these or be able to measure this occurrence in the field because normally a customer will just reset. But this is a much bigger problem in the return of warranty parts or driving hardware returns. And so this is one of the, I think, more significant aspects that needs to be thermal stress, and thermal HALT can do a very good job of helping produce these soft failures at a much higher rate. And I have observed that in IT equipment in many of the experiments I did. So here's a graphical way of looking at why we can be very efficient at detecting the problems during development that we're going to see in mass production in the field. When you are starting to develop a product, you have a very limited number of samples. And your distribution about a certain parametric value, for instance, is going to be fairly tight with just a small number of samples. You're certainly not going to see the very low failure rates, or hopefully you may have less than that, 5%, but and that could be significant considering what your product is. But it's going to be very hard to see that with 5 to 10 or so products. But with the fact that you're going to see variation when you start to produce mass quantities. As you increase the amount of the volume of manufacturing, your distributions of the components, you may use second source components. There'll be changes to the product, generally possibly in time as far as manufacturing processes. And what's going to happen is, as you increase this, you're going to get closer to the operating limits. And eventually, you may run into this problem where the tails of the distribution, or the most extreme variations, start to get into the operating limits of the capability of the circuit. Now, of course, you've got hundreds of components in a typical motherboard, all having some variation, and whether that variation is going to be a factor in reliability is certainly going to be due to what its function is in the circuit, how well it's centered in the circuit, and then, of course, the variation that will occur in manufacturing. Now here's an actual showing that shifting, the skewing that you can do with thermal energy. This was a Fairchild experiment with a Fairchild octo buffer to determine whether it could be upgraded and used. A commercial device could be used as a military part and you see the requirement of the timing limits here on the left. This is a propagation, the change in high to low propagation delay in this octal buffer. And at 35, you see that it has a certain lower speed or lower delay. And at 160, you see a much higher delay. As we say, it's almost a linear relationship. But this is likely true with all silicon. As the crystal lattice vibration increases, the impedance increases. So you actually have a ability to see what will be maybe a distribution about this value here. So the benefit of HALT and using HALT to its limit to define the operating limit is that as you heat it up, you increase the electrical impedance and you slow down the signal, as you saw in the previous slide. And you may, again, push that small group of samples into the lower operating limit and see the failure that you may see in the larger population in the field during mass production. And this could also be because of a component drift, for instance, over time, that it would cross into the non-op area. Of course, with cold, you can even, you get the same effect on the opposite side. You start to speed up the electrical signals, and you skew the timings to a higher speed. Again, you may reach an upper operating limit, and that can give you a good indication of what your risks are and the variation in the mass production population. And let me just say that I know Greg Hobbs used to talk about precipitation and then detection of screens or whatever. I don't believe in it's very useful or it's necessary to go above the operating limit, and basically, especially with thermal, you'll find that you have a significant amount of room to do testing under if you limit it to just the operating limit. Of course, you should expand those operating limits to the maximum capability, again, to the fundamental limit of technology. And of course, the follow-on to testing beyond spec, if it fails, why should I care? I mean, it's not supposed to operate there. Well, that's not really true. There's a lot of reasons for testing, being concerned about beyond spec. Customers, first of all, may use beyond spec. I don't know how many of you all know, but in the PC world and digital IT equipment world, generally 35 centigrade is the maximum specified using environment for the customer. Now, here in Austin, it gets well above 35, gets above 35 C up to 38, 39 on a hot summer day, and so you'd be actually violating the manufacturer's spec by using a portable computer or a desktop outside at 98 or whatever. And we know that, of course, customers do that all the time. People do that all the time. So you're going to get some use beyond spec. All components have margins to allow for manufacturing, and component manufacturers don't always, they're not always technical reasons for putting in a manufacturer's, the manufacturer setting a specification. It may be competitive pressure, market demand, and so, there's quite a bit of variation, and can be quite a bit of variation from supplier to supplier. And you don't know how much margin you're going to have or the effect of the margin or the limited margin is on the system without finding the empirical limits. Of course, margins can change in time. There is some, especially the RF components and some laser diodes, there is some drift and aging degradation. And again, you never know how the margin of the individual component and its variation will affect the operation of the whole overall system. It's not always the case that a component failing causes a system failure. I have observed in a system that had 28 of the same devices that the device was manufactured wrong, had a very early life wear-out mode, and in that 28 locations in the circuit, only three or four of those locations caused the system to fail. We actually couldn't get the rest of the motherboard to fail with the devices, the other devices all having failed. So again, not all components, component failure is not necessarily a system failure. This gets back to a real fundamental look at the whole purpose and reason behind HALT, and that is the stress-strength model. Along this stress-strength axis, you have a load, and of course you have a strength. And this can be referring to anything from bridges to electronic systems. As long as the load is less than the strength, you will not have failures. Now we know, of course, that there is a distribution about that. We have, for instance, on a VGA projector, some may be mounted on the ceiling where they would have a very low fatigue life. Others could be part of a road warrior's luggage, and certainly they're going to have a lot more fatigue. And at the assembly process, we have some that are going to have a stack up of tolerance that's going to be lower, and maybe at some with a different mix of components, it's going to have a high strength. The distance between these two is what we call the reliability margin. These are uncontrolled stresses. This is what the customer may use. It's very difficult to restrict his use. And of course, this is what we hope we reduce variation with SPC. As the product ages and the strength declines, we will have the two curves start to cross over. And as they do, the weakest links with the worst cumulative fatigue will start to fail. And it's really these tails, it's really the introduction of latent defects or an anomaly in the manufacturing process that for the most part causes the failures. Wear out is really not a factor in at least consumer electronics, and I'd say any electronics that's used 5 to 7 years that wear out. It's mostly because of mistakes in manufacturing, overlooked design margins, and abuse. So, of course, Dr. Deming taught about SPC and statistical and controlling your distribution. We all know about Six Sigma and the importance of reducing variation in manufacturing. And of course, that is an ideal goal, and we should, hopefully our suppliers are all doing that. But in a high volume manufacturing environment or in a rapid development of product, it may not be possible to have all your suppliers and all of their suppliers perform statistical process control. And of course, the end-use environment, well, we can give the manufacturing specifications, although, I mean, the end-use specifications, as I say, PCs, but they may be not known to the user or may be ignored. And of course, some are going to be, some systems are going to be subject to actions of abuse beyond the material strength. The question, the big dollar question, though, is when a customer, say, drops his cell phone or has a stress event with his product, where is he going to say, oh, that was a very flimsy product? Or where is he going to point to the himself and say, well, I guess I broke it? Either way, if it survives, you're going to have a very happy customer and certainly a returning customer, depending on his situation. Now I want to talk about stress boundary maps and what you can do with combining the empirical capabilities and starting to map out to determine operational reliability risk assessment. We usually do one temperature, a single stress at one time, but once we start and finish that, we start to add different stresses. Voltage and frequency variations are excellent in IT equipment. And so what we see here is a four-corner, typical four-corner test points, a high voltage, low temperature, high temperature, and on, so on. A little bit of V-rating boundary might be tested, but that really doesn't give you a clear picture of where you may have a problem or future variation. As you add samples, well, first of all, one sample, you're going to get one straight line, but as you start to increase the number of samples, you may start, and maybe a second source component. If you can do a few, great, the more the better. But you're going to start to overlay those, and you may start to see now a distribution in that boundary, a variation. And here's a good way of looking now that you have a map showing you the variations. You may see there's some very wide parts of your distribution in the empirical boundary map. And some of that variation, it may be far, it may be a large variation, but it's far away from the end use. You have very significant margin. In other cases, you may have a very wide distribution that gets a little more risky in the fact that these tails may start to actually creep into, and this can be, again, over time too, that these components causing this variation may start to drift into the actual worst case in-use environment and cause intermittent or failed operation. And gives you a place to start to investigate what is the cause of this wide variation in this boundary and see if you can reduce that with an increase, either increasing the margin or reducing the component specification to some way to reduce that variation in that boundary. And here's a time representative of putting this now, these variations on a time axis. We can now start to monitor. There's two ways to look at this particular graph. First of all, you can look at it from a production lot to lot. Here is the established beginning production. As you go through, you're certainly going to have a different boundary that, again, these these boundaries are a little bit dynamic. You certainly hope they don't change much, but the whole idea of HAS processes is to monitor those boundaries in time. But also what can happen with a component, it can also cause these boundaries to drift. In an individual assembly that you may have, again, the need to build up as much boundary, as much space, margin as you can to help ensure that that reliability margin throughout the product's life is going to be significant. As I say, there is so much life in standard electronics, solid-state electronic hardware, that we really don't need to be worried about calculating. We need to be worried about finding those things that impact the long life entitlement of electronic hardware. Okay. And the big question is, can HALT find software defects? And of course, I found out from my 7 years experience in IT equipment that yes, it can. I'd love to show you lots of data about it, but I will show you at the end of this an Intel case history about how they use thermal stress to find a software defect. I will give you some anecdotal evidence that one of the tests I did perform, I had the opportunity to take 2 computers, returned from 2 different customers from the field, and they had reported an intermittent failing, soft failure condition. Those were taken back to the failure analysis lab and spent 5 days trying to reproduce the failure mode. The units were declared in no fault found, or C&D, cannot duplicate. And of course, this is a big problem in the IT industry. There's a significant number of units coming back and a significant no fault found population. A lot of times those will go back to the field for repair as repaired parts or as warranty replacement parts. We placed those two units. I placed those 2 units in a chamber and cycled between 65 and -10, not an extremely high rate, but we reproduced the failure mode 3 times in a 24-hour period. So again, not all C&Ds are really C&Ds. With a little bit of stress, you can stimulate many of these intermittent and low-rate failures to show themselves and therefore give you something to troubleshoot. Can't fix the system unless you can find or create the problem. And this is the reason, we'll go into why thermal energy is so useful at helping with, as we showed before, the skewing of timings is a big part of the problems of operational reliability in IT equipment. So in the past, the bus frequencies were low. Nowadays, the light bouncing off your nose to your eye, it takes 10 times more resolution for some modern bus designs. The bus frequencies keep increasing, and here you see, of course, the ideal, a little bit of noise, and then the reality of the eye diagram now. And I think it would be great experimentation to see how this change of the eye diagram occurs in thermal stress environments. I think those would be an excellent way of developing discriminators and looking at marginal conditions or recreating marginal conditions in the product. Once you get overcome your fear of permanent damage or changing the performance characteristics of a product by reaching the operational limits, there's a lot of room underneath the limits to actually do significant application work and try things out, but you have to overcome the fear that you're going to permanently damage products. As these speeds increase, the effects of that were only second or third order before are now becoming dominant, and they may be very difficult to model in the time that we have usually in typical development cycles of commercial equipment. As we decrease, we see a decrease in the metallization widths and so on as Moore's Law continues. We're going to see more sensitivity to fabrication variations. Therefore, it's going to be much, I think, much more critical to tighten the control and monitor, especially the thermal stress, the ongoing production to make sure those variations don't interfere with the reliability. Looking at signal integrity and a very extremely simple model. Of course, today it's more of an 8-layer board, could be 10 layers, and correspondingly much more complex interactions. And of course, this is a typical cross-section. FR4 is still the common material, fiberglass. And of course, you have each conductor having its own electric magnetic fields, producing noise, crosstalk, interference, and it depends on the proximity, spacing, lots of different factors. Even the surface, copper surface, affects the inductance and resistance, and there are some trade-offs with that, of course, because you would like it would be ideal to have a smooth surface for the conduction, but it's got to be rough to make sure that the different layers, the adhesion between different layers is capable. Even the fiber weave effect now, you can't expect that the whole surface of the FR4 material is going to be homogeneous. You have a problem with moisture absorption, and the relative humidity can make a difference in signal insertion loss. So there's another variable that can affect reliability that would require pretty significant and complex calculations to know where you might arrive or where you might have problems in the future and in variations in manufacturing. So another aspect, and this of course is what helps create the thermal mechanical fatigue, so that if you do have an actual core solder joint, you are exercising it in a mechanical way and can get it to sometimes open up and be a detectable latent defect. But the fact that in heat we also change slightly the dimensions of the board as well as the impedance of the materials, we again kind of skew the whole function and some of the signals a little bit. And of course, in our manufacturing, we hope that the variation is only a little bit to ensure that we have a consistency in the signal integrity. With cold, of course, the opposite happens. We contract and we change the increasing speed impedance or decrease the impedance. And so we're stimulating some of the variations that will inevitably occur in the mass manufacturing of variations of lot to lot. And again, when we have an operational issue in a small number of samples using HALT, there's a very good chance that it will become an operational issue in some percentage of manufacturing product in the field. And I mentioned in HALT, you might, one of the important things to try is also thermal cycling. And the great thing about the HALT chambers is they can do a very rapid transitions in temperature. And of course, depending on the thermal mass of the devices, their power dissipation and other aspects, you start to get differential cooling in the transitions. So some of the larger components, thicker or heavier or higher wattage components may cool at a slower rate, higher rate. So you actually start to mix then the parametric shifting that you normally do or will occur in a mass manufacturing situation or a larger number of units being manufactured. And so therefore you're going to get some real synergy in these transitions, as well as, again, producing very high thermal differentials which produce higher thermomechanical stresses and therefore provide a more rapid precipitation of actual hardware, delamination, defects in the products. Now, as we quickly run through this as we're getting close to our end, I want to say thanks to Walter Fang for allowing me to use this, but also want to plug in for the workshop on accelerated stress test, IEEE, CPMT, Components Packaging Manufacturing Technology. I've been a part of this workshop since its inception in 1995, and I will be presenting a paper this year about some long-term thermal stressing of computers. Hope you all are able to make it. I'm the webmaster also, so check out the website, IEEE-ASTR.org. It'll be held in San Francisco at Fisherman's Wharf, September 28th this year. And we hope some of you will be able to join us, because as you see here, this is my, it's a core place where I get to see and we get to talk about actual reliability issues and the use of HALT and HASS. It really came about because HALT and HASS is poorly understood. Reliability information is very difficult to talk about because it's so sensitive to every company. So we try and share at least a few stories. They may be scrubbed, but here's a case of firmware corruption. Now, Intel uses a manufacturing stress test, MST. I don't know that these are set necessarily based on operation limits, but it's a very significant stress that occurs on these units. And of course, you see here they have a precipitation and detection screen. Not sure what the reasons were for that, but after the thermal cycling, they've started to see failures in the testing. And what they found was there's normally a function where the motherboard powers on and, for redundancy, backs up the current working data before a new flash information is written. And power cycling, which is an excellent tool in, especially in IT hardware development, uncovered a firmware design and it interacted, again, with probably a small tail of the distribution, causing an unrecoverable memory corruption. And of course, if you lose data, or that's pretty serious, and it obviously caused a problem. But only a few % of the product was susceptible. Again, this was probably the outliers of the tail of the distribution. So the actions taken to fix this was they changed the BIOS. And you know, I don't know the exact details, and Walter didn't give it, but I would guess there's probably maybe some timing aspect in that. But it was, again, an example of a stress test precipitating a software defect and a material and design marginality interaction. I'm sure once this flash was reset, it probably worked fine, and there was no permanent damage to the components. So again, you've got lots of life in components. You can stress them quite significantly and not have much degradation. And you know, you've got to start using those. Here's a Pareto chart that shows again some of the manufacturing stress test actions taken because of MST triggers. They do not correlate to the chart on the right. The list here is alphabetical. But you can see here that BIOS and firmware update was, as we've seen in the last example, was a part of it. And I have observed this also in my own experience in the field of the IT hardware, that there is a lot of advantages of doing thermal stress during the firmware and BIOS development periods. And you can get intermittent problems to show themselves much faster under thermal stress conditions than you can with at ambient on the bench.
Kurt, can you explain what MST is?
Manufacturing stress test. This was a test done during the manufacturing process, or this was like a screen. This was like a half screen, essentially, in the manufacturing process. This is not caught during development. And I don't know what Intel's use of HALT is during development, but most likely it would have been caught if it had been in HALT. Just showing that thermal stress can find software. So to come to a conclusion here, we want to review what we just talked about. Why test beyond specifications? Well, it's the fastest way to develop a reliable, robust product, and the fastest way to find all the weak links in a timely manner and introduce a mature product to the market at release. If it fails beyond spec, why should I care? Because, as we've seen in other slides, improving the margins, the thermal, and of course for portable products, obviously, improving the vibration and mechanical robustness reduces the warranty parts and customer dissatisfaction, obviously. I think intermittent problems are worse than an actual hard failure because you don't trust the product anymore. The highest margins result in the highest tolerance of variation in the manufacturing process. And the great thing in using it for vibration, making it robust allows for very high levels of stress to be used for screening. And higher levels of stress means shorter screen times, which saves you money. Also, for vibration robustness, you may save in packing materials. You may not have to use as much material to ship a product if you make it a robust, mechanically robust. And again, it's easy to do, or it's not necessarily easy to do, but it doesn't take many parts. It's usually one or two changes to a product, not the entire redesign, that allows for a very significant shift and increase in margin. We saw that it does, and there are some other papers out there that software defects can be found as well as hardware defects. So there is a double benefit in using HALT and HAS in that you not only can look for discriminators and find changes during the stress cycle, but it actually, of course, physically fatigues the product. So if there is a hard failure or a hard latent defect that will cause a hard failure, you'll be finding that also. We must overcome, everybody that hasn't done this yet must overcome the idea that everything is going to fail. It's going to be a big mass of melted metal and plastic, whatever, Generally, as you find when you start doing HALT, and over the 20 years that I've been doing it, it's sometimes very difficult to break a product, but you can always find its limits. And those limits are variable data that can be used for significant insights into comparisons of configurations, comparisons of potential components and subsystem suppliers. There's just lots of things you can do once we overcome the fact that we think that we're going to cause a massive destruction of our product. And I really didn't get into predictions of lifetimes, but failure prediction methodology, it doesn't work. It doesn't give lifetimes. It's not, for the most part, valid. There are some mechanical wear-out mechanisms that it is for, but those are few and far between. For solid-state electronics, the lifetime is more than you need. And again, just as an example with that table radio, it could be 30 years. Most of us will never know how long the actual inherent life of chips is today. I mentioned previously the many opportunities for reliability discriminators using prognostics, which is now the common term in the industry, prognostics and health management. And I think that we'll find many better discriminators under stress conditions than we have ever before if we take the new paradigm of HALT and HATS and the stress limit paradigm.
So I'd like to thank everyone for your continued interest in Qualmark's Ask the Expert series. Qualmark hosts these free webinars throughout the year featuring topics of interest for our accelerated stress test community. If you have a case study or other HALT HATS knowledge you'd like to share with our audience, please let us know by sending an email to events, EVENTS, @qualmark.com. These webinars are also posted on Qualmark's event calendar announcing upcoming events, and you can locate the webinar recordings on our library, which requires a one-time login username. So again, everyone, I thank you for your participation. We'll send the remaining questions over to Kurt, and he can contact you directly. Everyone have a great day. Thank you.